In this video, we're going to start looking at some specific reaction mechanisms and understanding the mathematics of those kinetics using the definitions of the rates and looking at rate laws for each individual step. So our first example we're going to look at is a common reaction motif where we have some sort of reactant here that reacts in one direction to turn into an intermediate. So I is our intermediate, A is just one of our reactants. So we form some intermediate, and then in a second step, the intermediate follows the second rate law, first order for both of these unimolecular, and turns into the product. And this is a common motif that's seen. And in both of these, in this reaction, of course, we could look at the reverse reactions, but we're assuming here that K1 is much, much bigger than K minus 1, and K2 is much, much bigger than K minus 2, meaning that essentially this reaction just proceeds in the forward direction, and there's no appreciable reaction going in the reverse direction. And so this is sort of the model we can take. Now what we want to look at when we're modeling kinetics like this is for each of these species that we're looking at, what is the rate involved with each of the species. So in this case, we have A, I, and P. We have our reactant, we have our intermediate, and our product. And we can write a rate equation for each of those. And this is a very common approach to take when you're given a mechanism to look at what is the overall rate law that you would expect. So if we look, for example, at dA dt, well, the only thing that has A involved is this forward reaction here. And so we can say this concentration is only going to change by A reacting from reaction 1. So it would be negative because we are losing A as this reaction proceeds. We could put the negative sign on the other side next to the derivative, but this just makes it a little bit clearer. And that's it. Our second partial, or not partial, but our second derivative here is how does I change with the function of time? Now here we have two different things. We have first I is produced as A reacts, so that rate will depend on A, right? So that's from reaction number 1. And then we'll have a negative from reaction number 2, and it'll depend on our second rate constant, and it'll depend on the concentration of I. So that is, we have two different processes that occur for I. We can have I being produced by A turning into I, or we can have I disappearing by when it turns into the product. Okay, and then the final thing is our product. What is the rate of change of our product over time in its concentration? And here we just have positive values, right? Our product is not turning back into reactants at any point according to this mechanism, and it depends on the concentration of our intermediate. Okay, so we have these three differential equations. They all depend on each other, right? So these are known as coupled differential equations. And these are solvable. The first one here, we've already solved this type of rate equation before. This is just a first order rate equation like we had in the last chapter. And so that one, given some specifics, right, we need to know specifics. So assuming that at t equals 0, the concentration of A equals A naught. So we have to have some initial concentration given this, and that we assume that there's no I or P at t equals 0. So we assume we just start with A. We have to make some assumptions here to be able to set limits on this differential equation. We've already solved this. So the concentration of A is just going to follow first order kinetics. So we have A is equal to A naught times E to the minus K1T. Right, so that's an equation that we saw in the previous chapter. We can also find equations that describe I and P. These, we will not go through the derivation of these, but we will look at the results. So the concentration of our intermediate, which depends on the concentration of A, looks like this. So we have K1 times A naught divided by K2 minus K1, and then we have two exponential terms. We have e to the minus K1t, and we have a negative e to the minus K2t. Okay, so that's our equation for our intermediate. Again, we didn't derive this. I'm just giving you the final results. And for the product, well, once we know A and I, we can say, okay, well, our product all had to come from our initial concentration of A naught. We subtract off however much A is still left behind, however much intermediate there is. This is sort of our mass balance, saying that our product didn't appear out of nowhere. It came from our initial concentration of A naught. And so we can just plug in these equations here. So this equation here for A, this equation here goes into I, and after we sort of simplify this, we get this equation. We get A naught times 1 plus 1 over K1 minus K2 times K2 e to the minus K1t minus K1 e to the minus K2t. Okay, so this gives us a way we can plot these. We can see what happens in terms of understanding, how does our concentration of A, it decreases exponentially. We have some I that will be produced and then used up, and so that'll sort of balance out. And then our product will grow in according to this this final equation here. All right, and we'll go ahead and pause the video here, and in the next video we'll look at some of the consequences of these equations and how we can tell a two-step mechanism apart from just a single step without an intermediate.